Hello, welcome to another module in this massive open online course on estimation for wireless communications. In the previous modules, we have seen the maximum likelihood estimate of the channel coefficient of a wireless communication system as well as the properties of the maximum likelihood estimate, that is the mean and the variance. Let us now look at a simple example to compute this estimate of the wireless channel coefficient to understand this process better. Alright. So, today let us look at a simple example for wireless channel estimation, a simple example of wireless, that is wireless channel estimation, as we said channel estimation is the process whereby you compute the estimation of the wireless channel coefficient. We have already seen the model for the wireless channel, that is the model of our wireless channel is given as, that is our wireless model or our wireless system model or wireless system model is given as Yk equals h times xk plus Vk, whereas we have already said and we have described it in the previous modules that Yk is your observation, the output at the receiver h is your channel coefficient, x is the transmitted pilot symbol, your x is the transmitted pilot symbol and Vk is the noise. Vk is the noise. So, we have this model Yk equals h times xk plus Vk in the wireless system, alright, and this describes the input output model of a wireless communication system. For instance, let us say we have a simple base station and a mobile receiver, that is a mobile. I have, for instance, this can represent a model where I have a wireless base station which is transmitting on the downlink to a mobile. So, this is my wireless base station which is the transmitter, and the downlink, let us say it is transmitting to the mobile, and therefore, I have the transmitted signal which is xk, the received signal which is Yk at the mobile, the channel coefficient which is h, and basically also we have additive noise Vk at the mobile. So, basically this is my mobile and this is my base station, and this is basically a simple wireless downlink scenario. This is a simple wireless downlink scenario where we have said we are saying that basically a base station is transmitting to a mobile. The base station transmits the symbol xk that travels through the channel with channel coefficient h, which is represented by the channel coefficient h, and the received symbol at the mobile is denoted by Yk, and of course, there is also additive noise Vk at the receiver. This is known as a downlink scenario because the base station is transmitting and the mobile is receiving. Correspondingly, when a mobile is transmitting and the base station is receiving, you have the uplink scenario, and also the transmission, the corresponding system model for uplink scenario is symmetric, where xk is the transmitted symbol by the mobile, Yk is the received symbol at the base station. Alright. So, basically this can be used to estimate the channel coefficient, the procedure can be used to estimate the channel coefficient in the both at the mobile in the downlink and also at the base station in the uplink. All right. So, now let us look at a simple example. Let us take some simple numbers to understand this paradigm better. All right. So, we said Vk is the additive Gaussian noise, and in previous modules we have also assumed Vk to be the 0 mean. If you remember, Vk is 0 mean symmetric complex Gaussian noise with variance sigma square equals 3 dB. Okay. So, this is 0 mean symmetric complex Gaussian noise with variance given by 3 dB. All right. So, Vk we are saying is complex additive complex Gaussian noise which is symmetric, it has a 0 mean and it has a variance of 3 dB. All right. Okay. So, and also now let the transmitted pilot symbols be given as, let the transmitted, remember we have pilot symbols being transmitted for channel estimation. So, let the transmitted pilot symbols be, the transmitted pilot symbols are x1 equals 1 plus j, x2 equals 1 minus j, x3 equals 2 minus j, and x4 equals 1 plus 2j. So, these are the transmitted pilot symbols. In fact, we have 4 transmitted pilot symbols, that is x1, x2, x3, x4. These are the 4 transmitted pilot symbols on the downlink which are transmitted by the base station on the downlink, all right, for the purpose of channel estimation on the downlink, that is the channel, the downlink channel is estimated at the mobile. Okay. So, we have 4 transmitted pilot symbols, and in fact, what we did is we stacked these 4 pilot symbols as a pilot vector, that is we have x bar, which is, if you remember, your pilot vector. So, the pilot vector x bar is now given as 1 plus j, 1 minus j, 2 minus j, 1 plus 2j. These are the transmitted pilot symbols. This is basically the pilot vector. This is basically your pilot vector. Now, let the corresponding received symbols, let the corresponding received outputs or the pilot outputs or pilot outputs, we said the received outputs or the outputs corresponding to the transmitted pilot symbols, which are also known as the pilot outputs, are given as y1 equals 3 plus 5j, y2 equals minus 5 minus 3j, y3 equals 2 plus 3j, and y4 equals minus 3 minus 2j. So, these are the corresponding 4 corresponding pilot outputs. So, what do we have? We have 4 transmitted pilot symbols x1, x2, x3, x4, which we have stacked to form the pilot vector x bar. Corresponding to each of the pilot symbols, transmitted pilot symbols on the downlink, we have the corresponding received pilot output or the observed pilot output y1, y2, y3, y4 at the mobile on the downlink, and now I can again stack these received pilot outputs as a vector to form the output pilot vector or the output symbol vector y bar. Okay. So, now I am going to stack these pilot outputs y1, y2, y3, y4, and that gives me that basically your output vector or basically your pilot output vector. Since these are the outputs corresponding to the pilot symbols, it is automatically understood that this is the pilot output vector y bar, that is this is denoted by y bar. So, writing this explicitly, my y bar is going to be 3 plus 5j minus 5 minus 3j 2 plus 3j and minus 3 minus 3 minus 2j, and this is basically your observation vector, output pilot vector, output vector, also your observation vector. You can call it by any name. And now therefore, we have the transmitted pilot vector x bar, we have the observation vector y bar, all right. And notice that both these vectors have complex entries, therefore, they are complex in nature. Therefore, the scenario that we are considering is the estimation of a complex baseband channel coefficient. Remember, the framework that we have developed, we said can also be estimated to a realistic scenario where the channel coefficient, that is h, is a complex quantity, and this arises because we are considering the complex, we are considering a complex baseband channel coefficient h that basically represents the complex baseband transmission model of the wireless system, of the wireless channel between the transmitter, which is the base station, and the receiver, which is the mobile for the downlink. So, we are considering a complex baseband transmission model, and correspondingly we have the complex channel coefficient h, and naturally we also have complex quantities such as the complex transmit pilot vector, which is x bar, the complex output vector, the complex observation vector of y bar, and also complex additive white Gaussian noise at the receiver. So, we are considering the framework for the estimation of a complex baseband channel coefficient h. Okay. And as we have derived the expression, the estimate of the complex channel coefficient h hat equals x bar Hermitian y bar divided by norm x bar square. All right. So, this is the estimate of the complex, remember this is the estimate of the complex baseband channel coefficient . This is the estimate of the complex baseband channel coefficient, and this is a complex parameter. Naturally, this is a complex parameter, and therefore, let us compute the quantities one by one. I have norm x bar square, which is the norm square of the pilot vector, that is given as magnitude of 1 plus j square plus magnitude of 1 minus j square plus magnitude of 2 minus j square plus magnitude 1 plus 2j square, which is basically 2 plus 2 plus 5 plus 5, which is equal to 14. This is magnitude norm of x bar square, that is we have derived the norm of x bar square, which is the sum of the magnitude, sum of the squares of the magnitudes for of each of the components of this complex vector. This we have derived as basically equal to 14. Now, let us derive the other quantity, which is x bar Hermitian y bar, which is in the numerator. Therefore, x bar Hermitian y bar, this is basically equal to the conjugate transpose of x, which is 1 minus j, that is you take x bar, take the transpose of the vector, and take the conjugate of each element, because x bar Hermitian denotes the conjugate transpose of the vector 2 plus j and 1 minus 2 j times the product, that is, this is x bar Hermitian, this is x bar Hermitian, which is basically we said take x bar transpose and then take the conjugate, and then take x bar transpose of the vector and conjugate, and then of course we have the observation vector y bar, which is 3 plus 5 j minus 5 minus 3 j 2 plus 3 j minus 3 minus 2 j, which I can write as, now taking the sums. Well, first I am going to write the real part. The real part turns out to be 3 plus 5 minus 5 plus 3 plus 4 minus 3 minus 3 minus 4. This is the real part, plus the imaginary part, which is minus 3 plus 5 minus 5 minus 3 plus 2 plus 6 minus 2 times j. You can check this through computation of x bar Hermitian y, and therefore, this is equal to 0, real part 0 plus imaginary part 6 j. So, this is basically x bar Hermitian, this is basically your x bar Hermitian y bar, and therefore, now we have computed both the quantities. We have computed the numerator, that is x bar Hermitian y bar. We have also computed the denominator, that is norm x bar square, which is also basically x bar Hermitian x bar. Remember, norm x bar square is also x bar Hermitian x bar. Therefore, the estimate of the complex channel coefficient h hat equals x bar Hermitian y bar divided by norm x bar square, which is basically equal to your x bar Hermitian y bar divided by x bar Hermitian x bar, and this is basically equal to, well, x bar Hermitian y bar equals 6 j, norm x bar square is basically, we have already calculated this, this is equal to 14. So, basically the channel estimate h hat is equal to, that is a complex baseband channel estimate h hat equals 6 divided by 14 times j. This is the estimate of the complex baseband channel coefficient. This is the estimate of the complex baseband channel coefficient. All right. So, we have derived the expression for the estimate, we have computed the estimate of the complex baseband channel coefficient, and h hat equals x bar Hermitian y bar divided by norm x bar square, which is equal to 6 j divided by 14. Therefore, the estimate is 6 divided by 14 times j. Okay. And now, let us also compute the variance of the channel estimate. Of course, we know that the expected value of the channel estimate is basically the true channel underlying true unknown channel itself, because we have said that the ML estimate, the ML channel estimate is unbiased. Let us now compute the variance of this computed channel estimate, and we have said that the variance of the channel estimate, that is what we have computed in the previous module, that is expected value of magnitude h hat minus h whole square, that is average value of the square of the deviation. Remember, this is equal to sigma square divided by norm x bar square. It has already been given that the dB noise variance, that is 10 log 10 sigma square. What is this? This is your dB noise variance or noise power, dB noise power or dB noise variance equals 3 dB. So, 10 log to the base 10 sigma square equals 3, which basically implies that sigma square equals 10 to the power of 0.3, which is equal to 2. Alright. So, the noise variance sigma square equals 2, which means the variance of the channel estimate. Therefore, we have expected value of magnitude h hat minus h whole square, which is equal to sigma square divided by norm x bar square, which is equal to 2 divided by 14, which is basically 1 divided by 7. So, this quantity is basically 1 divided by 7. This quantity is basically the variance of the complex baseband channel estimate. This is variance of the complex baseband channel estimate. Further, so we have computed the variance of the complex baseband channel estimate, and we are saying that is 1 over 7. Further, remember, we are assuming 0 mean symmetric complex Gaussian noise of variance 3 dB, that is of power 2, alright, which means because the noise is symmetric, complex Gaussian symmetric, therefore, it also means, as we have proved in the previous modules, that the estimate of the real and imaginary parts are basically uncorrelated. The estimate, that is, the errors in the estimates of the real and imaginary parts are uncorrelated, alright, and also both of them have an equal variance, which is half of the total variance of the complex parameter. So, therefore, since, and finally, this also implies, further we can say, since noise is symmetric, complex Gaussian, this also basically implies that your variance of real part of the channel estimate is equal to variance of the imaginary part of the estimate, and that is equal to basically half of the total variance, half sigma square divided by norm x bar square, which is equal to half 2 divided by 14 equals 1 divided by 14. So, basically this is the your variance of the real and imaginary part. So, what we have done, we have seen a simple example in which the variance of the estimate of the complex parameter, the net variance of the estimate of the complex parameter is basically 1 over 7, and the variance of each of the real and imaginary, the variances of each of the real and imaginary parts are equal to basically half of this net variance, that is half of basically 1 over 7, that is 1 by 14. So, what we have seen in this module is we have seen a simple example of a channel estimation procedure in action. We are considering the downlink wireless scenario where the base station is transmitting pilot symbols, the mobile is observing the corresponding pilot symbols, pilot outputs with knowledge of the transmitted pilot symbols, and also with the corresponding received pilot outputs, one can compute the channel estimate at the receiver, which in this case is the mobile, which is receiving the symbols on the downlink. Alright. So, we have seen, and in fact, we are considering a complex baseband transmission model in which all the quantities are complex, that is the transmitted pilot symbols, the received pilot outputs, and the noise samples at the receiver, all the quantities, and also more importantly the channel coefficient H is a complex baseband channel coefficient. So, corresponding to this simple example with the transmission of 4 pilot symbols and 4 corresponding received pilot outputs, we have computed the channel estimate, that is the estimate of the complex baseband channel coefficient H, which is denoted by H hat, and also not only that, more importantly, we have characterized this computed estimate in terms of the variance. We have computed the variance of the estimate of this complex baseband channel coefficient and also the variances of each of the real and imaginary components of this complex baseband channel coefficient. So, this example sort of comprehensively illustrates this process of channel estimation, the scheme for maximum likelihood channel estimation in a wireless system. So, we will stop this module here and continue with other aspects in the subsequent modules. Thank you very much.